Okay. So last time we, well, first of all, as a reminder, tomorrow is the first CS Tech Talk. So tomorrow we have at 4 p.m. It's out on the Bluff. Is a company from Madison, Aurora WDC, who has several of our former students working for them, as well as they have several computer science students who are interning with them. They're coming to give a presentation. Usually the Tech Talks are in the evenings, but this one's a little bit earlier in the day. It's at 4 p.m. Strongly encourage you to go and check it out. Listen to Eric Johnson give a presentation. I think a couple of his other management folks are also going to be there and talking about some of the projects they're working on with our computer science folks, and give you some ideas on what internships might be available and that kind of stuff. But strongly encourage you to go and check that out. A lot of them are going to be indoors, but this one happens to be out on the Bluff. I don't know the dynamics behind that, but go ahead. They're usually an hour, hour and a half. You know, then a lot of times maybe the presenter talks for 45 minutes or something, and then it just turns into questions and conversation and stuff. So I mean, if you can only come for part of it and take off, then that's okay. But I would definitely, this falls into one of those categories of things that often students don't take advantage of, and then I hear them in my office when they're starting their senior year wondering, why can't I get an internship? These are some of those opportunities where you can find internships or create contacts with some people who could then also go and help you find internships. These are, I think, important opportunities that don't cost you a dime other than a little bit of your time. Similarly, and I had posted this on Slack a couple weeks ago, tomorrow night at starts at 6 p.m. is the CU Launch starting night event. If you don't know what I'm talking about, you can go read about it on Slack. But it's a entrepreneurial type of event where you learn how to create business models around a piece of technology. Comes with free food. They give you a book called The Mom Test. So if you somewhere in your mind have kind of an entrepreneurial spirit where you want to maybe run your own business someday, or at least learn what that process is like, especially since businesses modernly are built around software pretty often, it's a good experience for computer science students to get involved in. So it's kind of, where does technology meet business? And I mean, you show up for 3 different sessions. The intro thing tomorrow night, then there's a whiteboarding session where you learn how to kind of create your business plan for your fictitious business's idea that's just in your head. And then there's a final presentation thing, and you can win up to $2,000 doing it. We've had plenty of computer science students do this in the past. You don't actually produce a thing in the end. Everything's about an idea and incubating that idea onto paper. So, you know, your time commitment's pretty low, but you get to learn about some interesting stuff. And again, make some relationships with some leaders in some industries around town. Again, could lead to internships, could lead to things like that. So strongly encourage you to also take advantage of that. If you are interested in that, though, you do have to send an email to Dr. Dan Sem, letting him know what your generic idea is, and you know, that way they make sure they have enough pizza and stuff. So if you did that today, it probably is not too late, but that is 6 p.m. tomorrow over in the business building right outside of the makerspace. So strongly encourage you to take advantage of that as well. Questions about either of those things? Okie dokie. So for today, we were to look at what Boolean expressions are. Last time we started looking at variables, this idea of how do we implement or how do we mimic human memory inside of our computer programming languages. We did that through variables, and because we are working with C++, which is a strongly typed language, when we create a container for holding a piece of information, we have to label the kind of value that that container is built for holding. So for example, if we wanted to create a variable called my age, for example, I have to advertise this guy is built for holding an integer. And then you can put the value of that guy in there. All right, so at this point, I have created a variable called my age. If I want to then go and print it, I'm going to switch back to IOStream here. I can print out what my age is. So there's that 21. But because it's a variable, its value can vary. I can then go and change its value to something else. And then if I print it out again after I've made that modification, I'll see that I have now updated my memory location. It is case sensitive. So if I named it my age with a capital A up here, I have to name it my age with a capital A down here. So now I've made a modification to it. So from this line forward, my age now holds a new value, holds the number 32. All right, that's the generic form of variables, remembering pieces of information associated with a name. Okay, so the next thing we want to look at, we talked about the way human beings solve problems. We remember stuff, we ask questions, and we do repetition. So the next two, asking questions and repetition, both require us to create a have some way of asking a question, some way of creating this idea of true or false. So that's where this idea of Boolean expressions come in. So a Boolean expression, this is any expression that boils down to a single value of true or false. All right. So I think I kind of gave a quick example outside. So I could say, last class rather, I could say like, it's cloudy outside. You look back there, you say, yeah, it's a true statement. It is cloudy outside. Okay. If I were to say it's sunny outside, that's a false statement. It's not sunny outside. All right. So anytime we can give a statement or an expression that ultimately comes down to a truth, either true or false, that we would call that a Boolean expression. And we use that to ask questions, right? You might decide that, like, should I go golfing this afternoon? Well, if it's not raining and it's warm enough, I might decide that, okay, it makes some sense to go golfing, right? So you can ask some questions like that, but we have to have a way of formulating those questions. And we have the ability to do that through Boolean expressions. Okay, so we want to be able to create, and we talked about this through our primitive types too. So back in our list of all of our primitive type variables, wherever we had it, this last one here is a Boolean variable. So this is a kind of value built for holding true or false. In an older language like C, these guys were represented as zeros or ones. We talked about all that computers like numbers, human beings like things that look more human to us. Let's see what version they have in their C++ library here. In C++, are looks like maybe it's bool. So let's call this guy is sunny is equal to false. Let's make sure I'm using the right syntax here for their vintage of compiler. Yep, I am. All right, actually, you can see it under the hood here, though. So I'm creating a variable called is sunny, but instead of this guy being built to hold an integer, like my previous examples, he's built to hold a Boolean. And in C++, the type for Boolean is called bool. In Java, it's Boolean all spelled out. In C#, it's I think it's bool like this. In an older version of C++, it was bool all caps because it was done through something called a macro. But in any case, this is the type of primitive type that knows how to hold trues and falses. whether we're seeing them visually represented like this, like a false. So C++ is actually an interesting, because we're seeing, if you remember, I think we have our picture here that kind of shows our lineage of our programming languages. So right now we're standing between these two languages. I'm saying we're using C++ because I want to use some of our little bit more modern libraries, but really, since we're not writing object-oriented stuff yet, we're mostly writing stuff in C. All right, but any way you cut it, these two languages are substantially older than these languages here, like Java and C#. So even though C++ has given us some mechanisms for, instead of storing trues and falses inside of integers, which they're actually held as under the hood, we now get this nice convenient type called a bool. That's great. But we're seeing here that when I actually went and printed out the value of isSunny. So I created isSunny as a variable. I said it's a variable built for holding a bool. And I went ahead and I put an initial value of false in there. But when I went to actually print it printed out as 0, showing us that behind the scenes, the value of the Boolean is actually numeric. All right. I'll go ahead and create a second value. I'll say bool, what do we want to call it, is windy. We'll set that guy equal to true, and I'm just naming it. This is just a naming convention. I'm calling it is windy, is sunny. Nothing keeps us from just saying Boolean B is equal to false. Syntax for variables is the type, followed by the variable name, equals the value, equals the starting value. All right, and I'll go ahead and print out is windy here. And we see that this guy gives me a 1. 0 is false, 1 is true. Officially, the way this was initially written in the old C language is 0 was false, anything other than 0 was true. But the way you typically will see it implemented is as 0 or 1, true or false. So we're right back to the idea of binary, right? The reality is that the Boolean type is likely represented as a byte, which is our smallest primitive data type. So even though we're only actually holding 2 numbers in there, a 0 or a 1, seemingly, technically the amount of memory that a Boolean data type is taking up behind the scenes is going to be 8 bits. So we could say a little bit inefficient, but our C language doesn't support the bit data type, storing a single 0 or 1, and neither does our modern computer architecture. So in the 325 class, when you learn about, Intel-based assembly language, like we looked at here, we start talking about the hardware registers that are on a CPU. CPUs don't ship with a bit size register, even though it might make sense sometimes to store just a single bit. The smallest size memory locations on our modern processors are byte size. Actually, they're short size. They're 16-bit registers, and you can use the high or the low side for 8 bits. Potentially, if you're representing, well, no, in a single register, let's say. If you're let's say I have a register that knows how to hold. So at this point, I'm talking about CPU. So this is somewhat unimportant for here, but they're very related. So if on my processor, I have a bucket that knows how to hold 16 bits, I can use that bucket to represent a value between 0 and 65,535, or a value between negative 32,768 to positive 32,767, the stuff we talked about, whether we're storing signed or unsigned values. So I can use those 16 bits to hold that kind of number. Or I could say, you know what, I just want to hold a whole bunch of trues and falses. So at that point, I can actually hold 16 individual trues and falses. I could say this is a 0 or 1, this is a 0 or 1, this is a 0 or 1. But then you have to play the game of, if I want to get this 0 and 1 out, how do I actually extract that from that 16-bit register? And we do that through something called bit shifts and things like that. Unimportant for us, but You know, the idea is that if I have a bucket with 16 little slots in it for holding zeros and ones, as a human being, I can choose how do I want to utilize that bucket. Make sense? All right, so we might say that the average way would be to store a single whole value, but nothing says I have to do that. I can divvy up those 16 buckets however I want and use them however I want. All right. So we're seeing in C++, we do have the convenience of referring to false and true, but under the hood, we're seeing that they're actually represented as numbers, which means we could actually do math with them if we decided that ever made real sense. It probably wouldn't make sense, right? In real life, we wouldn't say, oh, it's sunny, so go ahead and print out is sunny plus 3. We could, but that doesn't make sense. That remember, the programming languages are allowing us to solve problems similar to how we solve problems in real life. So just because something technically would be allowed because of the way it's represented, we don't need to do math with every number that ever exists. We're representing trues and falses with zeros and ones. And while we technically can do math with zeros and ones, that's not the purpose of Booleans. Booleans are for asking questions. Okay. Here. So conditionals. All right, so now we're going to look at conditionals. The ability to, these are typically done through if statements in our C-based modern programming languages. And so if statements, which require Boolean expressions to accomplish their task. So in C and C++ and Java and C# and Swift, in all those languages, the syntax for an if statement is what I'm about to show you. The word if, all lowercase, opening parenthesis, a Boolean expression, closing parenthesis, and I'll go ahead and use this dot notation. So now I'm going to talk about these curly braces here in a second, but for right now, we're going to say you always have to have an opening curly brace, closing curly brace. I usually will indent. And this stuff in here is where the logic goes when the Boolean expression is true. Optionally, we can have an else. And this is where the logic goes when the Boolean expression is false. You don't actually have to have an else, though. In real life, we don't always have an alternative. We might say, hey, should I go outside? Well, if it's not snowing, yes. I might not have an otherwise. I just don't go outside, right? I don't always have to have an alternative. Okay, so this else is an optional part of an if statement. But if we want to ask a question, we ask a question using the syntax if, all lowercase, opening parenthesis, some Boolean expression, where a Boolean expression is any expression that boils down to a single value of true or false. Okay, and I'm gonna keep saying it like that over and over again because we're gonna, as we start building things together using ands and ors, we're gonna build more complicated looking Boolean expressions, but at the end of the day, it still boils down to a single value of true or false, right? So I can say, if it's cloudy and it's warmer than 60 and the wind is less than 30 miles an hour, that's pretty fast wind for golf, but if you're downwind, let's say it's good. If all those things are true, then that single gigantic Boolean expression will boil down to true. If all those things line up, then I will go and play golf, something like that. Okay, so one of the things that we're going to have to get good at is when we see a Boolean expression in the wild, even if it seems very involved, there seems to be a lot of parts to it, as we start resolving those individual parts, it boils down to that single value of true or false. That's what makes it a Boolean expression. Make sense? All right, so this is the syntax for our conditionals. So we can go ahead and write something with that. So I'll say if is sunny. Now I'm going to write it what I would call fairly redundant initially, and then we'll talk about it. But so if I'm going to say if is sunny, if that variable is equal to true. And notice I have a double equal sign here. We'll talk about that here in a minute. Okay, so if is sunny is equal to true, then we can do something like it is sunny outside. Now, is sunny here is currently equal to false, right? So I'll come to this question right here. We will resolve the value of is sunny. Is sunny is equal to false. Is false and true the same value? It's not. So this is a false statement. So we will not execute the body of this if statement, because we only do the stuff in here if the Boolean expression boiled down to true. And since I didn't write an else here, there won't be something to do when it's false. So as I have this written right now, if I were to say, what's the output of this program? The answer is nothing. I have some stuff, I have some code, but what am I doing? I'm remembering two pieces of information. I'm asking a question regarding one of those pieces of information. And in this particular case, I get a false answer from here, so I do not do this. So the output of this program will have nothing on the screen. That doesn't mean the program's bad. It's a working program that just happens to not have output. I can put an else, so I can go out here and I can say else cout. Maybe we find something to do indoors. Something like that. Now I run that, and now we get that alternative statement. Since this was false, we don't execute that stuff, but we do execute what was in the else. One or the other, but not both. So with the conditional, if conditionals, if there's an if and an else, we will only ever execute one of those two. Now, if I change is sunny up here to true, I've just shifted the original value of that Boolean variable, changed none of the other syntax. Now is sunny is true. So we ask the question, if the value of is sunny, which resolves to true, if true is the same value as true, then I'm going to print out it is sunny outside, and I won't print out what's inside this else. So now I get a it is sunny outside. Make some sense? All right. One thing to keep in mind here, though, is the behavior of the else. This guy only happens if this is false. But if I take that code that's inside the else, and since I said the else is optional, and I instead just put that line of code after the if statement, but not inside the else, My program executes from the beginning of main to the end. All programs begin and end with main. So I start walking through this program one line at a time. I'm going to remember something. I'm going to remember something else. I'm going to ask a question. If it's true, I'm going to do this. If it's false, I'm not going to do this. But then regardless of whether this was true or false, I'm hitting this line of code right there. So that what I have highlighted there will always print out on the screen here, regardless of what the value of is sunny is. So right now I'm going to get a, it is sunny outside, and then I'm going to get a, maybe we find something to do indoors. I get both of those things. If I change is sunny back to false and I run this again, this will be false. Therefore, I will not do that, but I will still do this because there's no conditional guarding that line of code. That line of code happens. When we hit it, it goes.
So could the else have been a false statement?
The else have been a false statement. Yeah. Well, you can do something like else if is sunny is equal to false.
Oh, I mean, if sunny is true, and then if sunny is false, then display that.
Well, wouldn't that be the else?
Yeah, I'm just saying that.
Oh, so I get you. You want to just have a completely separate.
Yeah.
You want to have this. You want to have two separate questions that we're asking.
Yeah.
So if is sunny is false, then we're going to do this line. So yeah, that's technically legal code. We might say that that's, you know, maybe not, since these guys are very closely linked, right? This is effectively the else of this, the alternative of this, but nothing keeps you from asking two separate questions in real life, right? I could say, hey, if it's sunny outside, I'll print out it's sunny outside. Now, since it was sunny, we can say that this is sort of a wasted question, but nothing keeps us from asking it. We can still say, well, if it's not sunny outside, then we'll print out, maybe we find something to do indoors. So I can ask as many questions as I want, right? But typically, if we have things that are related to each other, we'll use a structure like an if else, where we say, hey, if this is true, do this, otherwise let's do something else. And we can even have multiple ifs stacked inside there, where we can say, if this is true, do one thing. If something else similar is true, do something else. If something else similar is true, do something else. Otherwise, nothing worked out. So we'll do, that'll be the alternative. And to kind of show you that example, I can do something like, maybe we say int a is equal to 3. And we could say something like, if a is equal to 1, see out, you win. Then I can say something like, and I'm going to write it in the way I would typically write it, but that'll allow me to explain this curly brace thing. Else if a is equal to 2, we might say rats on second. Else last place. So now I'm asking multiple questions here. I'm saying, hey, if a is 1, do this. If a is 2, do this. Otherwise, do something else. So in this case, a is equal to 3. So I will fail this, that is false. I will fail this, that is false. So I'll get inside this else and say last place. There's that last place thing. If I change a up here to 1, but don't change my logic at all, run it again, now I see you win. All right, now where I want to bring focus to here is in this else if. I've actually taken a shortcut here and sort of kind of broken my own rules I've advertised. And let me explain what I mean by that. Really, what I would do here is I would say else. Steal this stuff. If I'm following the rules that I've previously set out for the syntax of if statements, I've mentioned that you always need these curly braces. You don't actually always need the curly braces, and I'll explain why in a second. But this is a true statement. It is never incorrect to have the curly braces. So I recommend you always have them until you really, really, really know why you don't need them sometimes. So in this case, I've said an if will have an opening and closing curly brace associated with it. I've also said that an else will have an opening and closing curly brace associated with it. Nothing keeps me, though, from inside that else asking another question. This if has an opening and closing curly brace associated with it. This else has an opening and closing curly brace within it. This logic that I have written here is identical to what I had a second ago. Now, we would say that this seems a little bit more convoluted. So there's probably a decent reason why I omitted those curly braces before. So let me explain why that is now. This slide here is sort of kind of a lie. I've taken some liberties to make life a little bit easier, or let's say life a little bit less error prone for beginning programmers. The actual syntax for conditionals is if true statement. I'm sorry, if Boolean expression. Then what goes in here is my true statement. Optionally, else false statement. So whatever this single statement is the thing that's linked to this if the if statement here. Whatever this single statement here is what's linked to this else statement. So if I only have one single thing to say, I actually don't need to have the opening and closing curly braces. But let me show you why this can be problematic. We'll go back up to our stuff up top here. So technically, I can write that same code there like that. This is legal code. Okay. Sunny starts off as false. If Sunny is true, say this, else say this. No harm, no foul, will work just fine. All right, so now I'll add a second line there. And this line just prints out after the if statement and L. And now we're going to see when I run this, that line will print out. We are after the if statement. Now I have purposely indented this line so that it looks like it belongs to this else statement. Okay. In a language like Python, Python does not have the curly braces. Instead, Python relies on indentation to decide what goes with what. So if we were looking at this code in Python here, Since both of these lines are indented underneath the else, they both belong to the else. But in C-based languages, the curly braces are the way of creating a block statement. So a block statement is a single statement. So it would follow this syntax, Boolean expression followed by a single statement. But a block statement is kind of like a garbage bag that can hold a whole bunch of other statements. So it's a single statement that holds other statements. But in this particular case, I have not used a block statement. I've had my else and I've written two individual statements afterwards. And the second one, I happen to indent so that to our human eyes, when we glance at this, it looks like this dude belongs to this else. Okay. So we see here that with is Sunny being false, we fail this statement. So we get into the else and we print out, maybe we find something to do indoors, and then we print out the after the if statement. Thinking that, oh, well, maybe this guy is connected. So maybe if I change this to say maybe after the false statement, we might be lulled into thinking that this line only happens when this was false. This line always will print out after this line prints out, but never after this line prints out. But if I change is Sunny to true, this will be true, so it'll print out it is sunny outside, but then we will still get this line of code printed out because it doesn't actually belong to the else. This is just a line of code that happens to be down the line inside of main following that if else structure. So there's our after the false statement line. Okay. So this would be that example where I would say it's never wrong to put that opening and closing curly brace in there, even if you only have a single statement. Now it's much clearer that this thing is disconnected from this thing. Even if I indented it, you might just say, oh, that just kind of looks weird. Because one thing as beginning programmers, the one thing that you won't do that I'm strongly encouraging you to do is indent your code to make it more readable. What ends up happening is you're going to introduce bugs into your code when you're first getting into this. You'll have everything left justified. You'll put multiple things on the same line. C and C++ don't care. You can have this entire program. I can put both of those guys right there like that. C doesn't care. The semicolon tells it where the end of this guy is and the beginning of the next guy is. But we would say that this is much harder to read for a human being than the two lines of code like that, right? So I would say take some time, and here's my if statement. I have indented the stuff that belongs to that if statement underneath that if statement, as opposed to making everything left justified like that. That is harder to read, even though technically C doesn't care. Similarly, I can make everything left justified like this, and we would say that's also harder to read because now we can't necessarily tell that this stuff all belongs underneath main, even though C doesn't care. All right, so indentation to make your code readable by humans, including yourself when you're debugging your code, is an important skill. So take some time to do it. One thing you will sometimes see that has now become somewhat of a standard is instead of having the opening curly brace the next line down, you will see it up here like that. And that's consistent with what I just said, where C doesn't care. C is fine if you put your entire program on one big long line. Okay. And this has become somewhat of a standard. You will see this kind of interchangeably with what I think is the better way of writing it, where you have that opening curly brace lined up underneath the if, where you can see this is where it ends, this is where it begins, and everything inside it is part of it. So having said that, where do you think this syntax came from? where you had that opening curly brace up top. Go ahead. Okay. Computer programming has been around for a while, right? Longer than the internet? Yeah, a lot longer than the internet. So now if you are working, if you're looking for an example of some code, we would Google it, right? And when you get a web page, you get effectively an infinite length long screen, right? You can have 4 million lines of code, one after another, so you can just scroll down, no problem. Well, we used to have our code delivered to us in textbooks, right? By the way, notice I don't make you buy a textbook in my classes. So that saves you probably $75 or something like that. But if this code is in a textbook, you are limited by the number of lines that can be on a single page. So anytime they can compress the code up, you save yourself a single line by getting rid of this extra space there. Make sense? And they can say, okay, well, this is technically still readable. That's not horrible looking. I happen to think it doesn't look as organized as this, where you can see left justified where the beginning and end of that block is, but it's still okay.
Could the bottom brace be up there?
Well, you can be. I mean,
oh, like
yeah, you can put every single line here on one big long line. C does not care. Human beings won't be able to read it, but C doesn't care one bit. But we would say if I write it like this, this is less readable than that is. If I write it like that, this still kind of seems like it's a little pod that stuff in there belongs to the if statement. Go ahead. I would say it's personal preference. This or this are both acceptable. I would strongly encourage you to take on that format. Like I said, that other format was born out of trying to save a line in a textbook, and how it has become somewhat common for people to write. That doesn't mean it's wrong to do it that way. It just, its initial intention was for a different reason that we don't really have that problem now. Similarly, I would encourage you to always use an opening and closing curly brace rather than take advantage of the fact that, oh, well, technically, since I'm only doing one thing in here, I don't actually need that opening and closing curly brace, and I can just do that. And a textbook might have written this like that. Why kick it down a line? I can save myself more if I'm just going to ask a question and do something as a result. All that stuff is legal because all I've changed is the format of it. I haven't actually changed code. Make sense? C, C++, Java, C#, Swift, they're all completely cool with format changes as long as the code doesn't change. Python is an outlier in that, where indentation is extremely important in Python because a block statement with the curly braces does not exist in Python. They do it based on indentation. An older language called COBOL also works that way. Is there a question? Yeah. Okie dokie. So I encourage you to always use the opening and closing curly braces until you're very, very, very confident into knowing when you can and cannot use it. You'll thank me later with less errors. Okay. And I just think it looks better. I always use them, regardless of whether you need them or not. I think it just makes the code look a little bit cleaner. Okay. But like I mentioned, indentation, while not necessary in a language like C and C++, it is necessary in Python. So keep that in mind when you are exposed to Python in one of our classes, that Python's still a programming language, just like any other language, but it does have that nuance where indentation is an important part of the language. In fact, it's one of the few things I actually like about Python, is that it forces programmers to indent their code because you have to. Your code won't do what you think it should be doing if you didn't indent. But something like this, I would say, even though C is okay with this, the fact that I have indented it too much makes it seem like it's kind of part of this else. In fact, visually now, since I have the opening and closing curly braces, it just seems like it's weird having it sitting out there, where you should probably have things indented at the level where they belong. You could put an extra line in here if you kind of want to create more separation. That's okay. Doing something in fewer lines does not make your program better. All right. Now, if we rolled back to the 1970s or something where memory was really expensive and things like that, at that point, saving some storage space, not storing a carriage return, like I technically just had to store an extra \n in there. Technically, because I pressed return on that line. Well, back in 1970, that is taking up space and our hard drives were only so big when we saved the file. So that might be problematic if you do it too often. Today, that's not a problem. I mean, your computers have 1, 2 terabyte hard drives in it. That took up 1 extra byte. We're going to be okay. So I think especially as our programs are getting larger and larger and larger today, it's more and more necessary, more and more beneficial for them to be easily read by human beings. Because you aren't going to be, especially in industry, you're not going to be the only one working on the code base. You might be on a team of 20 other developers working on your little parts, and then you might get shifted over to a different part of that code where you're working with somebody else's code. And if they wrote it with the proverbial, what's called spaghetti code, where it's very unorganized and stuff, even if it technically works, if it's very unorganized and hard to follow visually for a human being, it's going to make your life harder. Okay. All right. Questions about the if statement stuff? All right, so let's look at Boolean operators. Well, we have multiple kinds of Boolean operators. So we're going to have arithmetic Boolean operators, and these you're already familiar with. So we've already introduced one of them, the double equal sign. This is the equivalence Boolean operator. Actually, I'm going to call it the primitive equivalence Boolean operator. This determines if the thing on the left-hand side is equivalent to the thing on the right-hand side, where those things are primitive values. They could be numbers, they can be chars, they can be Booleans, but they can't be things outside of what was on that list of primitive, our primitive types list. Because all of a sudden, if we're doing that, now what we're doing is we're actually comparing memory addresses. Still works, but probably isn't doing the comparison that you wanted it to do. And we'll see that by an example once we get a little bit farther down the line and start working with those. So the double equal sign is the equivalence operator, not to be confused with the single equal sign, which is the assignment operator. I am assigning this value to this variable with a single equal sign. I am creating a Boolean expression asking, is this primitive value equivalent to this primitive value? Make sense? And that will be a common mistake, as you might imagine, that you'll write 1 equal sign instead of 2 equal signs. And some programming languages will do it with a single equal sign, but I would say a majority of modern programming languages use a double equal sign because their single equal sign is for creating variables, assigning a value to a variable. And the double equal sign is used for testing equivalence because those languages were built in terms of C. So we have equivalent to, we have less than or equal to, greater than or equal to. Then we have this operator called not equal to. And you can't have spaces between these. So not equal to has to be one right after another. You can't put a space in between. It's a 2-character operator, not equal to. That makes sense? Go ahead. Also not legal. It won't work. Give you an error. That's just not something the language knows about. It's just a syntax error. Typically, these things are called reserved words in programming languages. So these are things that are meaningful to the language. So they're saying, hey, you're not allowed to, you can't use a reserved word as a variable name. So I can't say int greater than is equal to 4. Because that guy's built into the language and is already spoken for. Go ahead. Not in, well, actually in C. That's a good question. That would be a bitwise equivalent. I do not believe there is in C. We do have what are called bitwise operators. I think this is going to give us an error. Yeah, doesn't know about it. Yep. Less than. It said less than, equal to, greater than.
Yeah.
That guy, what did it say that operator was?
I don't know. It was on a list of C++ operators, and I googled it, and it said Ruby.
Yeah. So it's possible. Yeah. But you know, it doesn't let us do the mathy stuff we're looking at here. So I mean, there are weird operators in some languages, but I mean, you can imagine that a majority of the time, if we're talking about doing mathy crap, this is sufficient, right?
Yeah.
Less than, greater than, less than or equal to, all that stuff. Sorry, that was flipped around for the error message. Not equal to is how I read that. The exclamation point is the not operator. We'll actually see that on the next slide. Go ahead. It is. It's one of the logical Boolean operators. So my next slide here, and these are repeated down below. I just, when I created this slide set initially for the last time I taught the class, there's stuff in there that you'll see on the same slides again, but I just let it happen extemporaneously as we're going through here. So we have our logical Boolean operators. So this is the, we'll go ahead and start with the not operator. So not false is true and not true is false. So not just flips a Boolean. So not true, the opposite of true is false. Then we have the double ampersand. This is the logical and operator. Not to be confused with the bitwise and operator. This is something that you will not use very often. I'll give you an example of it probably next class, because you can imagine this might be a mistake that you sometimes make where you accidentally only put one of these instead of two. But this guy works on Booleans. Each side of the logical and, each side of the logical and operator has to be a Boolean expression. This guy works on numbers. It performs what's called a bitwise operation. I'll show you that to you next time. Somebody remind me to do that as an example. We'll stumble into it at some point anyways, but I'll show it to you. Then we have the logical OR operator. Similarly, we have the bitwise OR operator. Single pipe, vertical pipe. And then another thing that is a common thing, if you're in a programming language, you might decide, you know what, if I want to take some value to, if I want to say 3 to the 5th power, I might write it like this. That looks reasonable enough, correct? Put that on your calculator or something like that. You're going to probably get 3 to the 5th power. If I come in here and I tell this guy, tell me 3 to the 5th power gives me 243. That is not what this means in C and C++ or Java or C# or Swift. This guy right here is the bitwise exclusive OR operator. Exclusive OR. Operator. So just to kind of talk about those real quick in our last minute. When I say and, that's like me saying, oh, it's cloudy out and it's windy out. That's an and. That's a logical and. This is what you'll use 99.8% of the time. This is going to be a mathy thing. It is sunny out or it's windy out. That's what the logical OR is used for. You'll use this 99.8% of the time. You'll know what you're doing when you use this one. But when you accidentally use this one, this is where things go a little south. All right, that's why I'll talk about that next time. Same thing, the bitwise exclusive OR. Exclusive OR says one or the other, but not both. Okay, so exclusive OR says that if I say it's cloudy out and it's daytime, or I'm sorry, it's cloudy out or it's daytime, that's a true statement. If I say it's cloudy out, exclusive OR it's daytime, that's a false statement because both of them can't be true when right now it would be true. So exclusive OR allows me to say, is this my choice or is this my choice, but they both can't be right. Go ahead. Because OR says it's this one, or they both can be true. Yeah, OR says one or the other or both. Exclusive OR says one or the other. Done, not both. All right, so I'll just put a little, so we'll stop there. We'll show a little bit more on the Boolean stuff. You'll have a programming assignment over the weekend, our first programming assignment. So I would say for now, review what we did in class, make sure you're understanding what these Boolean operators look like. I will say start here. Wait, hold on. We're 12:50, right? I keep doing that. I keep doing that. Your first programming assignment will be over the weekend. All right, so we're good. But let me show you then how this bitwise operators work. So these guys work on numbers by performing the Boolean operation on the individual bits of the binary version of a number. So for example, if I said 7 bitwise OR 3, I'm going to rewrite that 7 and 3 in binary. So this is a 1, 2, that's a 7 in binary. And this is a 3 in binary. If I do a bitwise OR of those, 1 or 0 is 1. 1 or 1 is 1. 1 or the other or both. 1 or 1 is 1. So the answer will be 7. Bitwise, for each bit in these two numbers, I perform the OR operator. True or false is true when you're doing an OR. True or true is true when doing an OR. True or true is true when doing an OR. Seven bitwise OR 3. So want me to put it into a, actually maybe it will be okay if I just put it in parentheses here. So there's my 7 that came out of that. If I switch that around and I say 7 bitwise and 3. Now I'm doing that same math as I did before, but I'm performing an AND operator. True and false is false. True and true is true. True and true is true. So this will boil down to a 3. So 7 bitwise and will give me the 3. So until you know what is happening behind the scenes and you just start getting weird numbers, and it's even more scary in actually, let me make sure this is a true statement before I say it. Is sunny, is windy. Since they're numerics. Yeah, even worse. Because typically when we're using our logical Boolean operators, like I mentioned back here, a high percentage of the time, this is what you're going to mean, the double ampersand or the double OR operator. Basically, 99% of your life, you're going to mean one of those two. But if you accidentally use the single one instead of the other one in a newer language like Java, they would scream at us for that line. Because when we're dealing with the logical AND or the logical OR, the expectation is the value on the left-hand side is a Boolean operator, Boolean expression. The value on the right-hand side is a Boolean expression. Whereas the expectation is for this operator here, the left-hand side is a number, the right-hand side is a number. The problem is, as we saw earlier today, Booleans are actually represented as numbers. Newer languages like Java kind of have a special protection spell on Booleans and say, you can't do math with these dudes. Okay, so if I was in Java, it would scream at me for this line that says, look, that is a Boolean expression. This is a Boolean expression. This is a bitwise operator that requires an integer and an integer to work. Those are not integers, those are Booleans. But in an older language like C++, even though they're giving us a little bit of freedom by saying, look, yes, they're numbers, but you can say it's true or false. You can write those words and we'll do the conversion for you and store the zeros or the ones behind the scenes. That way, as a human being, you're not bothered by that. But it's still represented as zeros and ones and doesn't have that protection spell that I'm telling you is in there in Java, which means that you can do math with Booleans in C and C++. Not that it would ever make sense, but you could. Go ahead.
So for the 7 and 3, you did it. 1, 2, 3, this, bitwise or operator one, that is open to 1, 2, 0, or why is it 3 ones?
Hold on. We're talking on this guy.
Yeah.
When I had the or,
Yeah.
because or says one or the other or both.
Okay.
So true or false is true. True or true is true. True or true is true. Yeah. And I won't test you on the bitwise operator stuff. I'm mostly showing this to you as like if you stumble into this, this is what's going on. C didn't just roll the random dice and give you a number. Okay. There is rationale behind the scenes that is very much important in computer science, but also very much part of the 325 class. Make sense? Stuff's happening under the hood. There's a reason for it. I'm just hopefully saving you some time from an error message. Well, the bigger problem in C++ is you don't get an error message. You know, you use that wrong operator, you think life is good, but technically you had a mistake. Java will scream at you. Say, look, you messed up. These are Boolean things on either side. You did a mathy thing in the middle. That's no go. C++ isn't as friendly. Now, so you say, well, why did you make us use this less friendly language? So you'll appreciate the more friendly languages later on. All right, we're learning that, we're building that strong foundation. Is there a question? Go ahead.
And just ask what would you use it as for if you
Yeah, it's actually related to something I said earlier in class, where he was asking, well, could you use those 16 bits to store like 16 individual trues and falses instead of one 16-bit number? So you can actually, it's called bit masking. You can use the bitwise operators as well as these shift operators to shift bits left or right to extract individual bits from a 16-bit number, for example. Yeah, so it's for pulling stuff out of a hardware register where you stored more than one value just because you had the space. But unrelated to what we'll have to do in here, so not something you don't have to stress that this is going to show up as some random test question. I want you to store it away in your head somewhere as, hey, wasn't there something about using a single operator instead of two of those guys? And something bad can happen. Just kind of remember that. So when you run into the bug, you'll figure it out. All right. Oh, sorry. Go ahead. Okay. So let me do it like this. Let's see, how do I want to write it? I'll write it this way. So we have these things called truth tables. And the reality is you already know the answer, but you just don't have the context for it. So it'll make sense once you see it. So I'm going to create these truth tables. So we'll have the truth table for the or. All right, so this is just the concept of one or the other. So you heard me say today, one or the other or both. So with an or, you're always comparing two things. An or is true if either one of these things or both of these things is true. So I'll write it as zeros and ones, but I'll also put underneath here, this is a false. This is a true. All right. So these aren't finalized yet. I just made the answers green right now. So a 0 or a 0, where both things are false, the answer is false. A 0 or a 1, when at least one of the things is true, the whole thing is true. A 1 or a 0, when at least one of the things is true, the whole thing is true. A 1 or a 1, when at least one of the things is true, this is with an or, the whole thing is true. Okay, that is the truth table for ors. The truth table for ands is the inverse of that. Both sides need to be true in order for the result to be true. Okay, you might say, if I'm hungry and I have enough money, I'll go to Culver's. If one of those things is false, you're probably not going to Culver's, right? Because the and doesn't work out. Like, okay, I'm starving, but I don't have the cash for Culver's, so we're going to go card swipe into the calf. Something like that. Okay, so an and, both things need to be true in order for the entire thing to be true. So 0 and so false and false is false. False and true is false. True and false is false. True and true is true. So with an and, the only way to get a true is when both sides are true. And the last one is that exclusive or, which says one or the other, but not both. So that means that this guy right here in an exclusive or is false. When both sides are true, an exclusive or says, no, it had to be one or the other. It couldn't be both. Okay, so these are the tools that allow us to ask questions about truth, hence the name truth tables. Go ahead. For which one? For XOR, yeah, when it's exactly 1. So when there's a 1 and or a 0, it's a 1. When it's a 0, XOR 1, it's a 1. Otherwise, if neither of them or both of them, it's a false. No, you can build it with ands and ors. Yeah, you would build it. Yeah, but the reality is for us, just like I said earlier, a very high percentage of the time when you're programming, you're not going to use XORs. And a very, very high percentage of the time when you're programming, you're going to use the double ampersand or the double vertical bar, doing normal ands and ors, not the bitwise stuff. Okay, so the bitwise stuff is me showing you what's under the hood. It's a 325 thing. That'll be something we'll talk about next semester quite a bit when that's our focus, not programming. Questions, comments, concerns, bribes. So spend some time wrapping your mind around all this stuff from today, because you will have your first programming assignment over the weekend. I'll give you just enough to scare you on Thursday, and we'll go from there. No homework for Thursday, other than make sure you understand what we talked about in class today. Yep.